Okay, so we've defined convolution. Now let's look at several properties of convolution. Now, for us, convolution has a specific meaning. It allows us to find the output of any linear time invariant system given the input and given the impulse response of the system. But we could also define convolution just as a mathematical operation between two signals or functions of time. And so I use this notation, it's standard notation, use an asterisk to represent convolution. So in some of your computer science classes, you may in some computer programming languages that represents multiplication, but if you see it in this class, it is always convolution. So from the last lecture, we had the convolution of x1 and x2 is the integral from minus infinity to infinity of x1 of tau and x2 of t minus tau. And again, in the previous lecture, we wrote this in terms of the input and the impulse response. But again, we can take this to be actually a mathematical operation. You can show, and I'm going to state most of these properties without proof, that convolution is commutative. So x1 of t convolved with x2 of t is equal to x2 of t convolved with x1 of t. Okay. And so that means in this integral expression, I can swap x1 and x2 in this integral expression, and I'll get the same result. Physically, what this means is that if we have a system with impulse response h of t and input x of t, I could build another system whose impulse response is x of t, and then apply as input to that system the signal h of t, and I'd get exactly the same output. It's distributive, okay, across the sum. So x1 of t convolved with the sum of x2 of t plus x3 of t. And this proof is fairly simple because that integration operation is a linear operation. This is equal to x1 of t convolved with x2 of t plus x1 of t convolved with x3 of t. Okay. I guess the physical interpretation here would be if I think of x1 as the impulse response, and then x2 and x3 as being an input signal, or their sum being an input signal to that system, then the output I get when I apply this sum signal is exactly the same as if I applied the individual signals x2 and x3 to identical systems with impulse response x1, and then added the outputs. I get exactly the same result. And then it's also associative. So x1 convolved with x2 and x3, that's equal to x1 convolved with x2 and then convolved with x3. And then what this means is, if we have a chain of systems, again with maybe x1 as input and x2 and x3 being impulse responses of two systems, we can get the output by convolving x1 with the impulse response of the first system, and then convolve that with the second system to determine the output of the two-system chain. Alternatively, we get the same output if we convolve the two impulse responses of the two systems and then convolve that with the input. With the commutative property here, it means that we can actually do this convolution in any order. I could swap x3 and x2, or even swap x1 and x2 and call x2 my input. So if the systems are all linear and time invariant, we can interchange their order and still get the same result. Another property is the shifting property. If x1 of t convolved with, x2 of t is, let me call that w of t, then if I time delay x1 by capital T and convolve that with x2, the result is a time delayed version of w. Similarly, if I delayed x2 by capital T, I get the same result. Okay. A delayed version of the original output. If I delay x1, say by t1, and x2 by capital T2, I get then the original function delayed by both t1 and t2. Okay. Let's look at another property, convolution with an impulse. X of t convolved with an impulse, and you can prove this from the convolution integral is equal to x of t. So convolution with an impulse produces the original function. Of more usefulness is if we convolve x of t with a shifted impulse, that produces a time-shifted version of the signal. And this is a property that will pop up quite frequently, so it's worth committing to memory. Okay, let's take a look at what's called the width property of convolution. And this is very useful for determining the width of an output pulse if you convolve two pulse-like functions, or two functions of finite duration. So if x1 of t and x2 of t have width t1 and t2, then the waveform you get from convolving these two signals has width or duration of t1 plus t2. Related to this width property is, I don't think this is covered in the book, but I call it the starting time property. If pulse x1 starts at time t1 and pulse x2 starts at time t2, then the starting time of the convolved result is actually t1 plus t2. And similarly, there's a stopping time property. T stop, if x1 stops at time t3 and x2 stops at time t4, then the convolution result will also have finite duration and will stop at time t3 plus t4. You can show that this is actually this start time plus the durations of the two pulses. And again, t start is t1 plus t2. So let me show you just a simple example here. Let's say x1 starts at time 2 and maybe goes to time 4. I don't really care what it looks like here. It's just some finite duration pulse. And then x2 of t, let's say starts at, I'll say it starts at 1 second and then goes up to 6 seconds. Okay. So the duration of x1 of t is actually 2 seconds. 4 minus 2, and the duration of x2 of t is 5 seconds. So from the width property, we know that the duration of the convolved result is 7 seconds. But using the starting and stopping time properties, I know that the convolved result will actually start at 2 plus 1, or at 3 seconds, and then it will end at t equal 10 seconds, 4 plus 6. So 10 seconds. Don't really know what it looks like, but I do know it starts at 3 and ends at 10, and we can see from this that it does have duration 7 seconds. So as we're doing these convolution properties, or convolution problems, these are some important properties to help you determine whether you've gotten the right result. You know, look at the start time, look at the stop time, check the duration when you're dealing with these pulse type signals. Of course, if x1 of t is something like a unit step, which is infinite in duration, the output would be typically infinite in duration as well. And then the final property I want to look at here is causality. This simplifies our integral. If the system is causal, we know that h of t is equal to 0 for t less than 0, and in that case we can simplify the limits on our convolution integral. H of t minus convolved with h of t. This becomes integral from minus infinity to t x of tau h of t minus tau. And again, I won't prove this now. We'll look at this in a little bit more detail. We'll see what this h of t minus tau looks like. You may remember from circuits, it's a time reversed and shifted version of h of t, but for a causal system, h of t minus tau will be 0 for all tau greater than t, and so we can change our upper limit to t from plus infinity to t. Another way to write this, again, because we know that we can interchange the order of operation here, and I can convolve h of t with x of t. I could also, in this case, with h of tau here, and x of t minus tau. I know that h of tau is 0 for all tau less than 0, and so my lower limit changes from minus infinity to 0, and my upper limit in this case is infinity. If the input signal is causal, so we usually reserve the description causality for a system, but we have previously defined causal signals as being those signals that are 0 for t less than 0. Then our convolution limits simplify further, and we have the top integral above becomes an integral from 0 to t of x of tau h of t minus tau d tau, and then the second integral becomes an integral from 0 to t of h of tau x of t minus tau d tau.